I'm purely coming from the geotechnical side in terms of how the buildings and footing systems work in relation to the soil and the interaction. Now, I'm not an engineer, I'm a geologist, and I've worked in the geotechnical industry purely in Melbourne and Victoria for nearly 29 years. And I've, in that time, just specialised in doing soil testing for the construction of mainly domestic, but some smaller commercial buildings, and also developed a specialty in the investigation of movement and damage to damaged or distressed buildings. The presentation is broken down into three parts. The first part is just some basics of the soil and site investigation processes, and also some basic principles for soil science. Probably most of you will probably know that, but again, the focus will be on the geotechnical aspects of it, not the agricultural, arboricultural aspects of it. Part two is the common causes we see in that cause movement and damage to lightly loaded structures, and then part three is the solutions for building near trees, and something that we've got to educate our industry on is also protecting the tree as well. Okay, firstly, soil testing for our industry is a bit of a misnomer. We don't actually do, for domestic building industry, we don't actually do physical lab testing. It's just a hand classification method. It's called the visual tactile method, which you do in the field. And this is basically how you do it. The practitioner's got to be able to identify the soil profile on site. If they can't do that, they shouldn't be out there. Lab testing is only used really in court cases because the principles of Melbourne soils are pretty well known from a geotechnical aspect. So now here you can go to sleep if you want. I'll just go through this fairly quickly. These are, again, these are just the physical components of soil from a geotechnical perspective. It's got nothing to do with the nutrients and the value of the soil, as you were discussing before. As it was said before, soil testing is a bit of a black art, and a lot of engineers don't understand it, and they're scared bejesus out of them because they don't understand that it's not a definitive science, and that's why it's called the black art in our industry. The physical components of soil are basically broken down into three: sand, which is the larger particles, 60 to 2,000 microns, silt particles 2 to 60, and clay particles, which are much, much finer. They're basically the three building blocks or physical building blocks of soil. And all different soils are made up of different proportions of those same components. It's pretty rare that you'll get a full clay. It'll always be a silty clay or a sandy clay or something like that, but that's how we describe it. Now we describe the material content in terms of the major component is always mentioned last. So a sandy clay is a soil that's got more than 50% clay, but some sand in it. So the descriptor is the sandy. So you don't really often get silty sandy clays, but that basically means it's predominantly clay with less than about 45% sand and then some minor silt in it. Moisture content. This is important from a geotechnical point of view, particularly with reactive clay soils. The moisture content of a clay soil particularly is affected by different factors that interconnect. Clay chemistry and material content both have an impact. In our industry, engineers are often naively asking for moisture contents when they've got no idea what they're asking for. And it's one of the most complex areas. It doesn't sound like it is, but it's one of the most complex areas of our field. We tend to talk about moisture contents in clay relative to their plastic limit. The plastic limit basically is the moisture content of the clay, which it starts to change from a solid plastic material, which is mouldable, to a solid. And the simple way that Dominic taught me to do this was if you can, I'm talking about in-field situ, not adding any moisture. If you can roll a worm in a sample of soil that you got directly out of the ground to a worm about 3 millimetres, there's a lab test that does it between glass plates, but you can do it by hand if you know what you're doing. And if you can roll it down to 3 millimetres, it's about its plastic limit. Now, if we just keep thinking, but that's the plastic limit that we're talking about, which we're really interested in from a geotechnical point of view, and I'll tell you why in a sec. The moisture contents vary, as I said before, for all different clays. And this is where it gets tricky. pick 28%, which we often, it's a number that we use. In one type, a 28% moisture content in one clay type can mean something completely different. The same 28% can mean something completely different in a different clay. Around Brighton, the Brighton Group sediments are sandy clays, and their PL, the plastic limit's usually around the low 20% range. So if we're asked to do a soil moisture test and it comes up as 28%, that means it's 8% above the plastic limits, which means that it's wetter than normal. We'd be expecting it to be a couple of percentage points either side of its plastic limit. It's in winter time, it's a few percentage points higher than the plastic limit. In summer, it's a few percentage points drier. So 28% moisture content in Brighton clay, it's wetter than we expect. Now, Keilor clays, the Western Suburbs clays, are full volcanic clays. So their plastic limits are usually around the low 30% range. So the same moisture content, measured moisture content of 28% in a Keilor clay, means it's drier than we're expecting. So when an engineer rings me up and says, what's the moisture content? And you go, why do you want to know? And they go, I want to know it's wetter or drier. And you go, well, wetter, drier than what? Because they don't understand it's relative to the type of clay that it is. This brings on to the next bit. This is the most important bit of our soil sciences, which is the reactivity or the shrink swell components of reactive clays. It's the number one issue in terms of building new footing systems and also the performance of existing footing systems. The sandy and silty clays, because they contain so little clay and not really reactive, so they don't really suffer volume change with moisture variations. All clays do have reactivity, and that's just that they do suffer volumetric change with moisture content, and they swell when they get wet and they shrink when they get dry. Again, this is the number one problem we have with footing performance. And as I said, different clays have different reactivity. The reactivity is just basically determined by how much of the other components it has. The more sand in it, the less reactive it is. And also the chemical makeup. Some of the sodium clays, Montmorillon and isolite, are much more reactive. That's because of a difference in clay chemistry. This is a great photo that a friend of mine took on a tailings dam. This is a sign of reactivity. Now that's a full clay because it's been manufactured, but that's what we're talking about when we're talking about reactivity. It's the shrink swell nature of the clay, and I think that's a full illite, so that's why it's cracked so badly. But that shows you the measure of how much the volume can change with moisture variation. There are other factors that can affect the performance of a footing system for a lightly loaded building other than the soil type. And these factors generally affect moisture levels, and it can be the drying action of trees or the leaking pipes causing variations. Now, the new draft or the new version of the Australian Standard AS2870, which is the standard that applies to the construction of domestic buildings, footing systems, it requires us to identify the non-soil site conditions that are relevant, like trees or poor site drainage or whatever it is. But this is a ridiculous thing. The deemed to comply footings, which are adopted in this standard, which is Australian-wide, assume that those abnormal factors don't occur. So if you're going to adopt a deemed to comply, which every builder quotes on, a deemed to comply footing system, the standard, the brand new Australian standard, assumes that the top condition will apply. All right? I'm sure most people in the audience would think the bottom situation is a far more likely situation. People building new houses, first thing they want to do is plan around them. Now this code has just been amended in 2011, and it still says the standard deemed to comply footing assumes no one's going to plant any trees anywhere near the house. It's a ridiculous system. Now, one of the reasons that the Code Committee and the people in power that they did it that way was because the actual percentage of failures or cracking in houses is relatively small. It's less than 4%. Now I'll discuss later, we can come up with solutions to build near trees. The problem is that they've decided that with such a low percentage failure rate, it would be too much of a cost impost to put on the 96 or 97% of the rest of the houses that don't suffer damage to have a footing system that would be completely compliant with all situations. As I said, AS2870 expects that the soil test will identify the adverse abnormal moisture conditions, and that they request us to make a judgment on terms of what to do about that, which is fine. We can come up with a solution which we'll talk about later. This is the next point we're talking about outside. The code doesn't require us to consider the future situation on the block of land. You're not to recommend or design a footing system for a future condition that may or may not occur. Again, I don't agree with it, but that's the way the standard is written at the time. Okay, this moves on to the next bit, which is our area of specialty, which is the common causes of damage to low-rise buildings in Melbourne. Again, the most common causes of volumetric change, the reactivity of the clay soils based on moisture changes. That then focuses what are the main causes of moisture changes that create those movements. I've been looking at damaged buildings for nearly 29 years, and the figure's probably close to about 3,000 individual cases. Now, my experience is that the main causes of the moisture variation that leads to significant damage. Now, this is prefaced on the basis that we only tend to look at houses with significant damage. We don't tend to look at houses with minor damage. But our work has indicated that the major causes of the moisture changes are trees and other vegetation, and also the local wetting up of the soil as poor site drainage and plumbing leaks. There was a common commentary during the drought that, especially from one large architectural company, that all the cracking in Melbourne was caused because of the drought. In actual fact, my experience is that very, very small numbers of houses were cracked solely because of the drought. All of them were influenced by the drought, just about, but almost none of them were caused predominantly by the drying action in the drought. Now, contrary to popular engineering opinion, which I guess you would believe how widespread this is in the engineering field, all cracks in buildings are not caused by trees, because the engineers think that they are, and most architects as well. But the assumption that trees never cause cracking is also not correct, so probably the answer's somewhere in the middle. This is the thing that I've been concentrating on giving talks to geotechs and engineers, is that the assumption that just because a tree is close to a building, it's going to definitely mean it's going to crack. It's just not true. I reckon there's more situations where there's large trees close to buildings where there's no movement and cracking than the other way around. The assumption that a tree near a building is always going to cause cracking is just wrong. So this is a common scenario that we see when we go out doing soil testing. A house, good condition, and a well-established tree right beside it. Some photos to follow here. This is a house we looked at that did have some cracking in it, but the cracking wasn't at the front of the house. The front of the house was perfect, and this is the environment around the front of the house. So our recommendation in regard to that house around the front was to do absolutely nothing. Make sure the trees stay healthy. But if you showed that photo to an engineer, they'd say you've got to cut the trees down, even though there's no damage. Another example for an extension going on the back of this, that back corner of the house beside the window, I had a really good look around, no sign of any movement at all. Same thing. No sign of brickwork distress, no sign of floor deflections, no sign, but the assumption would be that the tree's too close to the house, going to cause damage. This one this morning, I actually did a soil test on this lady's house. Took this photo because I was coming today. She's putting an extension on the front of the house, which we're going to have to do something for because the tree's there, but the front of the house is perfect condition. So she asked me what to do about the tree, and I said, yep, just make sure it stays healthy. Because if that tree comes down, she could have issues. This is a typical crack pattern that we see from a tree drying point of view. You tend to get a diagonal pattern of cracking up and towards where the drying is occurring. The clay on the outside of the footing system is shrinking relative to the clay underneath the inner part and causes that subsidence to occur. This is the same house I showed you with all the trees at the front, which just goes either principle. We can't apply both ways. So the back of the house is rotating off, and the soil's super dry, full of tree roots, that was a fairly significant drying issue as well. That's probably at the upper end, the category 4 crack. But again, we tested the soil directly underneath that point and it had plenty of bearing capacity. It was probably 15 percentage points, maybe 12 percentage points under the plastic limit, so really, really dry. This is a case we're asked to look at by another geotechnical company who are getting into trouble. But that's just another indication. I think that if it close up of the crack, yeah, you can see that's quite a significant crack as well. That's a typical sort of crack pattern when you're getting a drying action underneath one end of a building. Probably just as important in terms of the soil being too dry causing damage, we also get a lot of houses where we get local build-up of moisture and it causes the clay to swell or heave, and that can cause damage as well. This is a typical crack pattern when you've got a leak coming in one side or poor site drainage causing the clay underneath the outer side of the building to become wet. When the reactive clay gets wet, it swells, lifts, and the adjoining section of the building tends to stay where it is, so the brickwork in the adjoining section where the heave's not occurring goes into tension. So to release the tension, you usually get a horizontal crack in the brickwork. So if you compare that crack pattern to the crack pattern before, which was a step crack pattern, the crack pattern can tell you what the cause of the problem is in conjunction with other evidence. So that's a typical photo of a house that's suffering from heave. Now the heave is occurring to the left of the photograph. So the section of building to the left of the photograph is moving upwards due to a leaking pipe. This section of the building, the soil moisture content is relatively stable, staying where it is, and because the next door piece of the building is going up, it's causing that brickwork to go into tension, which has caused the horizontal pattern of cracking. Really common cause where you've got excess moisture. Now some common misconceptions. You can't wet any of the Melbourne clays up enough to make them fail underneath the load of a domestic building. They always maintain enough shear strength to be able to support the building. So a crack pattern, when you've got a step crack pattern like that, and it's often maintained in reports that we see that that's been caused by softening of the soil because of a leaking pipe or poor site drainage. From a geotechnical point of view, under a lightly loaded structure, it does not happen. And this is why. The load conditions placed onto a footing create stresses that go down into the soil, like in the shape of a light bulb, which is called the bulb of stress. It's about, the depth of that bulb is about 2 times the width of the footing. So a lightly loaded structure, a house say, requires a bearing capacity of 100 kPa, which is about 1 kilogram per 1 square centimetre, which is me on one heel, basically. That's what the requirement is. In actual fact, the buildings put down about 1/3 of that. So if you can stand on the soil without sinking up to your ankles, it'll be enough to support a house from a loading point of view. Loading is just about, a bearing capacity failure is just about irrelevant in domestic buildings. I've used this drawing lots of times in court cases when people argue that it's subsiding because of dampness. The problem with that argument is that the clay underneath the footing is in a confined state by the other clay around it. So if you're going to try and explain it's going downwards because it's softening because of water, you need to explain where the clay underneath the base of the footing gets displaced to, because all the clay is the same density. So for it to be displaced, it would have to squeeze up and out at ground level. Now if you could put enough load on the brickwork to make the clay squeeze out the surface, the bricks would explode under compressive strength before the clay would give way. The only issue where this does happen is where someone comes along and does an excavation of a basement or a trench right next door to the footing and creates a void into which the clay could move. That's an issue. But when you've got a fully confined clay, bearing capacity does not occur. The other thing that we see quite a bit is the cause of movements. The building's moved and cracked because it's got an old bluestone footing. Now that's not the case. The effect of the lighter weight non-reinforced footings is that they just they concentrate the movement more directly because they don't have much of a spanning capability. Like, we now understand the reason for a footing is not to support the load from the building, because you could dig a clay in trench and lay bricks on it from a loading point of view would support the building. The purpose of a footing, we now understand, is to deflect the movements, the soil movements that occur over a greater distance of the wall, so that the movement's deflected over a greater distance, which means you get less distress. Whereas a bluestone footing or a weak mixed rubble footing, which has got no spanning capabilities, tends to deflect on a much, much shorter basis, and you get much more significant cracking. Now, the top is a representation of an unreinforced footing and the bottom is a reinforced footing. It's important to note that the mechanism of movement is still the same. The mechanism of movement is soil movement. The effect of the footing type is it exaggerates the distress because it concentrates to one area. So it's got nothing to do with the actual fundamental cause of what the distress is being caused by. It's just an exaggerating factor. Now, this is another problem which I guess you guys will have seen as well. We need to address it in our industry because there's a lot of reports on distressed buildings that are not based on a proper evidentiary base. If you're going to get one, it needs to establish clearly what the cause of the damage is. We're going to put a code together, hopefully it will be reasonably widely accepted through the industry, to try and get a standardised base that if the report's done in accordance with that, you'll have some reasonable confidence in it. And the basic things that we're going to include, it must do measured moisture contents because that's really important from a diagnostic point of view. Even though bearing capacity is not likely to be the cause, it's still got to be checked and eliminated as the cause. And in doing that, you've got to check the founding conditions of the existing footing, and you've got to make an assessment of soil reactivity. We see lots and lots of these reports based mainly on engineers and architects who just do walkthroughs and say, yep, that cracking is caused by the tree. No soil testing, no measured moisture analysis, no checking bearing capacity. And there's been some, well, I'm telling you, there's some really significant trees removed based on those sort of reports. In the reports that we do, the conclusions are going to be based on evidence from multiple sources, and you've got to get the sources all coinciding in terms of what the cause is. So if you're looking at a tree drying problem, you'd be wanting moisture content that was definitely much, much drier than the normal level, and a crack pattern that was consistent with drying, and also confirming the bearing capacity. So you're getting multiple sources of evidence giving you the same conclusion. Again, the report's got to be objective and it's got to be forensic. It's got to consider all the potential causes, and each potential cause that's not supported by the evidence has got to be eliminated. And then ultimately what you end up is with, after the investigation, is the only causes that are applicable. We've been using this method for a lot of time, a lot of years in Melbourne, and it's worked well. In terms of the remedial works for most distressed buildings, they're not actually that invasive. The first step is to identify and address whatever the cause is, usually related to moisture variations. The second phase then is to monitor the movement until the moisture levels return to a long-term equilibrium. That length of time varies, but it's going to need probably at least one full change of seasons, at least. And then once the movements have stabilised and we've established the original footing is okay and the bearing capacity is okay, most often the distress can just be cosmetically repaired. We've had some clients recently that it's been determined that the cause was significant trees. The cracking was not that bad. Once they're armed with the information that the cracking is not going to get a lot worse, because if the clay is close to its maximum dry potential, the potential for it to go much further is not that bad. They value the tree much more highly than they worry about the cracks. So once they're informed what the cause is, they do nothing. And that's completely okay as well. You just got to convince the owner that some cracking is normal, or a price you pay to live in a nicer environment. Some people accept that, and some people don't, especially in Caroline Springs. Okay, this is the last part. So we were discussing this outside before about protecting new building works. This is the engineering solution that we see all the time. They say, that's it, you've got to cut the tree down, and then you can use a standard footing. Irrespective of all your arguments, which completely legitimate and I accept them all, there's a major geotechnical problem with this solution. If you cut the tree down, significant trees particularly from a site prior to construction, it takes a long time for the clay to regain a long-term moisture equilibrium. in that period of time, the clay is going to swell because the drying effect of the tree's been removed. Now, if you put a footing system on the clay that's been dry because of a tree's been there for a long period of time, and we've seen many, many cases where this has happened, the clay swells and causes enormous damage. So, and that also applies to the installation of root barriers. Engineers, particularly in some lazy geotechs, just do a soil report that says use standard deemed to comply footings, which we spoke about before. Just put a root barrier in, you'll be right, no worries. The problem is, again, the same time delay applies with the root barrier. To be effective, you need to put the root barrier in 6-12 months before you start building to allow the soil to rehydrate before you can use the standard footing. No one has got that amount of time in a building situation to allow time for the soil moisture levels to return to a long-term equilibrium. But there's a better way. We've used this method for probably nearly 3 decades, and it's a much, much better way to address building near trees. You either use screw piles underneath the side of the building closest to the trees, or deep board piers. The important thing about these is that they need to go down deeper than the drying influence of the trees. And the good thing about them is it's an instant fix. Once they're in, there's no time delay, you can build straight away. And people they can plant whatever they like next to their house from a geotechnical point of view. The other good thing about screw piles and board piers, as distinct from root barriers, is that they're only isolated footing, so they don't cause a lot of damage to vital roots. Because if you're digging a big root barrier, sometimes there's really limited space in an urban block of land. They'll cut the barriers too close to the tree, and the tree will end up being compromised. Whereas these systems, if you have a shallow footing system supported on deep screw piles or board piers, down deep enough, it overcomes the problem instantaneously. Now, this, I think, should be actually incorporated into the Australian standard. It is, by the way, that they say that we've got to identify the soil moisture conditions and then recommend this system. The problem is the majority at the cheaper end of the building, people don't want these recommendations because they're costing them more money. So they're building all these deemed to comply footings knowing that people either have or are going to plant trees around the house. And yeah, it's just not an acceptable situation. And Dominic and I spend a fair bit of time at VCAT and County Court in these sort of situations where the builder hasn't done this. And the cost of these, the cost of board piers for a tree, I mean, you're talking maybe 8 or 10 piers that you might need. It's $2,000. Do you know what I mean? Cheaper than a root barrier, doesn't hurt the tree, and the house is permanently rectified. The only issue with it is that you can get differential movement between the section where you've got piers or screw piles and the non-piered section. And the way to overcome that, which has been accepted practice for a long time, is to include extra articulation in the building between the piered and non-piered section. We've been using that for easements, building near easements, for 100 years, and it's been fine. You still get some engineers though saying, if I pier one side because of trees, I want to pier the whole thing. But they're quite happy to put piers under one side because of an easement, but as soon as trees are involved, they want the whole thing. This is an example of two of our jobs. We got asked to do the soil test for the right-hand building. The other building was in existence about 5 years ago. The trees were present, and despite what the building looks like, the builder's actually not a bad builder. He, on our recommendation, put piers underneath the south wall of that building because of the neighbouring trees. About 3 years later, we coincidentally got engaged by the owner of the property on the left because he had some damage in his building. The north wall was rotating out fairly significantly towards the north. The building that we put the piers under was perfect, so that the trees are about equidistant between the two buildings. So that's an example where a deep piered footing system, they're not trees of that big a significance, but it obviously didn't affect the trees, and for a small cost the building was completely protected. The sad thing now is that the neighbour next door, I think, cut the trees down, but the owner of this building doesn't know why he had the piers anyway. So. This is a barrier that we got asked to look at. I won't tell you where. You don't have to. This is I was thinking about why you actually asked me to look at this. I'm worried. This was the second installation of this barrier. Yeah. And it had been in for a couple of years, and there's been issues with the building just outside of shot on the right-hand side. And it was redug and had to be done again. And what they didn't tell us was there's on the left-hand side of the trench there is a 400 millimetre high pressure gas main. Not on dial before you dig. Luckily the guy doing the excavation was a really good operator and he picked it up. These are the roots on the building side of the barrier after a couple of years. So completely breached. But in a situation where you've got an existing tree, you don't have a lot of other alternatives. You've just got to try and do the best that you can to get it in without causing disturbance. This was a bit of a trap. I went inside the house first and it looks like it's a tree drying problem, and actually it wasn't. It's a drying issue, but what had happened is that the people had a leaking downpipe at that location for 40 years, and also an old hot water system that had been adding water to the soil. They were fixed, and then this happened about 6 or 7 months later. So yes, it's a soil drying problem, but it had nothing to do with tree drying. It was just drying because people fixed. And people don't understand that any action that you have can affect soil moisture. Variations can have an impact on footings and buildings, either way, dry or wet. This is a typical crack pattern. And you can see rotation of the front wall of the cornice. We see this in a lot of houses. This again is wall rotation away on a moderately reactive clay site in Ringwood. Quite significant rotation, and that's the reason. Manchurian pears, like, I'm not a tree expert, but man, they've been causing us a lot of problems. So, well, I didn't know whether it was because the fashionability of them had increased or because people plant them in groups, but a forensic arborist came down from Sydney.
It's the rootstock they use.
Yeah, she said they're grafted onto really aggressive rootstock, which makes sense because they seem to be drying much more than you'd expect. Again, typical crack pattern because of soil drying. And another one, that's a quite severe one. That was a significant street tree. I actually wasn't engaged to look at that one. I was just walking down the street and saw it. It's a bit sad, isn't it? That's the wall rotation. The articulation joint's actually working as such because it's going to be relatively easy to fix because it's moving on the joint. But again, we did a soil test at the base of the wall, which you've got to do if you're going to investigate these, and that's what we found. High bearing strength clays, probably 7%, 8% drier than plastic limit, and full of tree roots. Okay, this is just about finished. In the good old days, we used to get engaged by Housing Guarantee Fund and insurance companies, and the funding was there to go back regularly to sites, and this is when that decade, or those 2 decades, is where we probably learned most about crack building because we got to go back on a regular basis. This is a classic where we had some step cracking in the garage. You can't quite sit there below those lights. Some vegetation in the front was causing some soil dryness. That was the crack when we first looked at the building. Root barrier was installed, and I think one of the sort of nondescript trees was cut down, but then a really good barrier was put in. That's what the crack looked like in June 2009. That's what it looked like in February 2010. That's natural rebound because of isolation of the drying effect of the tree from the building. That's probably one of the best recoveries. We had that owner was ropeable that she had cracking in the house, and when it ended up like that, she was really, really happy. We don't always get 100% recovery like that, and we don't know why. So, something to learn about. Okay, they're the conclusions. From a geotechnical point of view, soil, and particularly soil moistures, are much more complex than they seem. Performance of footings for lightly loaded buildings is determined by soil reactivity rather than soil strength or footing type. They do have an influence, but they're not that important. To be relied upon, technical reports relating to footing failures must be based on objective forensic geotechnical investigation, which should be cross-referenced. And all cracks are not caused by trees. There are far more situations, and I look at a lot every time I do a soil test, where there's situations where there's big trees close to buildings and there's no cracking, than the other way around, just that engineers think it's the other way around. So that's it, thanks.